preparing to live stream for YouTube and Facebook.
Give me signal, Doctor, to start.
Please check the loud, because there's some loud sound, some noise come. Okay. I can make a very short introduction, then you can come. Hello, everyone. Today we are continuing our Connecting Expert webinar series. I'm Ömer from Region 8 YP Subcommittee, and today we will do our 25th Connecting Expert webinar for this year, and totally it is 69th of the Connecting Expert webinar series. And today our guest is Aditya Taneja from Omicron Middle East, Saudi Arabia, and the moderator will be from Western Saudi Arabia section, Western Saudi Arabia YP member Ibrahim. And now I am leaning towards to them, and Ibrahim, you can continue with your webinar.
Thank you. Dear guests and dear students and dear engineer Aditya Taneja, welcome to our webinar. Today, we are extremely proud and honored to take part in this IEEE Connecting Expert program. I'm Ibrahim Al-Muhaysin, an industrial relations coordinator in IEEE Western Saudi Arabia section. I be the host of today's webinar. And our speaker today is Engineer Aditya Taneja, expert in Omicron electronics Middle East. So our topic is an interesting topic in power system, or especially in all level of power system. It's about on-site non-intrusive intrusive testing of AC circuit breaker. I will leave actually the floor to you, Mr. Aditya, to introduce yourself, because you will do better than I. Everybody in the audience, feel free to ask any questions at the end of the presentation. Now the floor is yours, Mr. Aditya.
Thank you very much, Sir Ibrahim, and thank you for this, giving me this platform, giving us this opportunity to talk to professionals here, young professionals, young students who are soon to be professionals. So I'll try to give some insight on this topic, that is non-intrusive testing of high voltage AC circuit breakers. So quite a lot of jargon there. I'll try to keep my content very audience friendly. If you have any doubts or questions, please feel free to stop me and ask further. I am a regional application specialist at Omicron Electronics Middle East. I'm currently in Bahrain, and I'm streaming live from Omicron office in Bahrain. And here my role is to support our customers in choosing the best way how to test their circuit breakers, optimizing their testing and maintenance activities, and supporting them in using our products, and also writing technical papers like this, and talking to audience at large like this, with webinars, with training courses, and all these things. So that's my job. That's the brief about my work here at Omicron. Professionally, I have completed my power engineering from National Power Training Institute in India, and it was focusing on electrical power. And after that, I have done my postgraduate program from Indian Institute of Management, Kozhikode, and currently, like so far, I have worked with projects ranging from 11 kV to 765 kV here. So I have some knowledge. I will not call myself an expert. It is a goal which I would also like to reach somewhere in future, inshallah. And here I'm here to share some experiences and some insights with you on high voltage AC circuit breaker testing and how to do it in a safe manner. Before I go into the content, I would like to share a very personal story, because I'm talking to students and young professionals here. So when I was a student in college, we used to have such big books on transformers and protection relays and generator design and operation and all these things. And circuit breaker was kind of one chapter in the electrical book. And we never used to give much attention to that, because it was considered to be, normally working fine, and most of the time don't create any problem and operates when it needs to be operated. But when I came into professional life, I saw that all the work that a protection relay does of analyzing the fault and artificial intelligence and all these algorithms which identify the fault, if the breaker does not operate and clear that fault, all the work done by the relay is gone into vain, and fault will keep propagating, and it will end up either damaging expensive equipment, or create losses for the utility which is operating that network. So it's an important topic. That's I would say, after coming to the field, I saw that it is equally important and quite complex. It's not easy. Trust me, ask the people who are testing these things on field. It's quite complicated, and our job here at Omicron is to try to make it as simple as possible. I will not say it is a piece of cake, but yes, it is. We are trying to make it safe and easy to do that. So let me go into the topic now with that little information about myself. And sorry for the light. Someone just switched off the light. People are leaving office, so someone did that by mistake. It will not happen again. So yes, this is what we know from our studies about a general overview of power system. We use some form of energy converted into mechanical energy to drive some kind of a generator to operate, to generate electricity, which is then stepped up, transmitted across a distance to the consumer at the end. It can be industrial consumer or domestic consumer, whatever. So there is broadly a generation technology, gas turbines, water, wind, solar, big topic now in our region, nuclear. Then there is a transmission system, and then there is a distribution system. There are a lot of details in it. No need to go into that for our discussion today. But what we are going to focus here on these two little black lines here. These are basically circuit breakers which are connected before and after the transmission line, or before and after any part of equipment to operate whenever needed for maintenance, or whenever needed for clearing the fault. So we see they are quite common in substations to have them, and they are of various kinds. And I cannot, if I just go into the different designs and technologies which are available for circuit breaker, I would need 2-3 hours only for just listing out the things which are there. So what I'm facing today, or what I'm covering today, is AC high voltage. So that already kind of gives you a window. High voltage means in IC definition, everything above 1 kilovolt, and AC means that it is not DC. So you can imagine there are low voltage breakers, which I'm not going to talk about, or they are not kind of covered in the topic today. And there are DC breakers also, which I'm not covering. Those are having different technology altogether, and need a different way of testing and maintaining them. So what we see here is just, I tried to give you a glimpse of the variety which is there in the market. So on the very left, we have very old 1960 designs of dead tank oil circuit breakers. These are like these tanks were filled with oil, and that was used for cooling the arc and operating the breaker safely. And then we have minimum oil design, which was an improvement on this one. Then we have vacuum ones here. Then we have air, again, very old design. And then we have SF6, which is currently the most dominant technology, which is there in high voltage. High voltage means above 66 kV. This is the most dominant technology. And below 66 and 1 kV, vacuum is the most dominant technology. Yeah. And then there is this new design of a substation itself, or this whole whole bus is encapsulated in an SF6 filled compartment, which is called GIS, gas insulated switchgear, which has not only the circuit breakers, but also the CTs, VTs, so on and so forth, buses, and everything is there. So we see this very common in Saudi Arabia, in most of the GCC, and they are replacing the old type of breakers which are there. Still, they are being replaced, and new ones are coming all with these GIS. So I will give some more focus on this while talking about my testing things. And this is not enough. So there is too much of variety of high voltage breakers also. So I cannot just give you a very simple overview there. However, I will try to make it small, and let's see what a circuit breaker is required to do. In a static condition, when it is not moving, it is required to carry the operating currents and insulate the high voltage paths from the ground. So there is a high voltage part, there is a ground, it should provide the insulation between that. And it also should isolate the faulted parts to the grid. So in case the breaker is open and there is a fault here, this part is this part of the grid is okay, or whatever is connected on this side is okay, then the breaker should provide insulation between the faulty part and the healthy part of the network. So that is the static behavior. And dynamic behavior is while it is operating, from open to close, on close to open. It should make and break operating current safely, make and break fault current safely. So this is a very good definition, or a very good way for an engineer to look at circuit breaker as an equipment which is able to perform these two behaviors. And with this, I can now try to make a very functional model, or a representative model of a breaker, in which I say that, let's say this is a breaker which is a 2 break per phase SF6 live tank design breaker with spring mechanism. But I can use this particular model to create a generic model which I can use to classify other breakers also. So there is something which is interrupting the main currents and main voltage, which I call interrupter units. Whatever is inside that, that depends on the type. So first thing is interrupter unit. Next is the support insulator, which basically supports the main structure and provides a housing for the linkage mechanism to move the breaker contacts. And then there is something which is having the operating mechanism. So just a second. Yeah. So there is something which has operating mechanism and control. So where the command from the relay will come, and it has the spring or whatever is the mechanism to store the energy that is there. Now with this, I can take this very simple functional model to other breakers also. May it be GIS, may it be vacuum. I can go back and relate the same things to those breakers. I'll not go into taking this to other breakers, but this is a model which I will use for my further discussion. Other thing, while doing the maintenance, we generally do the inspection test every 6 years. This is not only the visual inspection. Visual inspection is done every year, but this is inspection like without opening any circuits, without doing any changes in the breaker condition when it is in operation. We try to do some tests to know the health, and this is what my focus is today. This is where we want to do non-invasive measurement. We don't want to change any connection, open any circuit to do the maintain to know the health. And while we do that, we can know, if we know that there are some problems, then we can take it for a maintenance based on the condition, or we can leave it there and we do a complete overhauling after 12 years or 10 years. These numbers are indicative. Local authorities have their own cycle which should be followed. So this is where I'm coming from, the inspection test. And also there are some things which are focusing on the maintenance as well. And the idea is to not to test every year, not to do a very detailed test every year, because that is just wastage of time and effort and resources. So the idea is that whenever we do the testing, it should be enough to increase the increase the time intervals between subsequent tests, so that your system does not get shut down every time. You don't have to take it out and all this extra effort which are required to be done to take a shutdown and get a permission to do testing. So that's an objective which we want to have. Now let's look at the model again, the functional model which we developed in the previous slides. And so we have the interrupters, mechanical linkage, operating mechanism, and control. And how do we see when we are doing the maintenance or when we are doing the inspection, how can we make sure that we are doing enough tests on these parts to know that when I put it back into service, it will not fail for next 6 years, for example, or next 3 years, whatever is the frequency. So there are different types of behaviors which or type of problems which are faced in interrupters. The main is the wear and tear, because it is operating in high current environment, high arcing environment, which is quite stressful for a breaker contacts. So we need to see the wear and tear. That we can check by doing dynamic and static contact resistance measurement. So this is one test which we should do, both of them actually, because high voltage breakers, they have an assembly of main and arcing contacts, and main contact health can be seen by static resistance measurement, and arcing contacts can only be seen by dynamic contact resistance measurement without opening the circuit. I'll talk about these tests in detail. Then for performance of the kinematic chain, the mechanical part, if it is working properly, there has to be some distance which it is moving, and it is doing that in a certain period of time. So distance and time are main criteria for checking the performance of this mechanical part. So we do timing tests, and also we should do travel test. Both of them together will give you um, a clear picture of what is the like if there is any slack in the, if something is not working properly, like dampers, or if something is worn out, you will see it here. Then we do the testing of charging motor, because we have a operating mechanism there which can be different for different breakers: spring, pneumatic, hydraulic, magnetic. So many of them are there, but they are all mechanical and they are very specific to the vendor, and it is very difficult to check its health. Health means basically lubrication, because there are a lot of moving parts. 50 to 100 moving parts are there, which cannot be visually inspected. So what we do is we check the overall performance by analyzing the motor current. So whatever is the motor which is charging it, if the lubrication is not good, the resistance will be high and it will draw more current to charge that particular mechanism. That's the basic thumb rule. So that's an analysis which we can do. And also we do the performance test of control circuits. So the logic which is implemented, like when the breaker should operate, under what conditions, under what interlocks, and whether it is working within permissible limits or not. If the protection functions are working, there are some protection functions to make sure that the circuitry does not get affected by high voltages or impulses. All of that has to be checked. And the most important one is the trip coil and close coil, which takes the command from the relay and propagates it to the operating mechanism to operate the breaker. So that needs to be analyzed more in detail. And and there are multiple tests which are there. There is an under voltage test and over voltage test to make sure that these coils work in boundary condition, not only in the nominal condition. Because if there is any chances of failure, it will first start showing in the boundary conditions. That is the upper limit of the coil operation and the lower limit of the coil operation. And also there are some minimum pickup tests to make sure to know what is the force needed for the coil to operate, because that force is proportional to the overall health of the coil. Again, these coils are small copper wire coils which are having a moving part inside, and they are very sensitive because they are not high rated, they are very short time rated, they have to be very quick, so they are very delicate. So the force which is needed is proportional to the current, and we try to check that with minimum pickup tests. So this is a kind of a framework where you can see that what you should consider while preparing for a maintenance for breakers. And this is not enough, actually. This is only a part of electrical test. Then you have some insulating features also of the breaker, that is insulating between contacts and ground and between the contacts. So you have to do, the standard says you have to do AC high voltage test. But normally people do DC high voltage test, and they do the insulation resistance between the contacts, between contact and ground, and between phases. But that is also okay. So that is there. Then check the health of the insulating media, SF6 density, and all these things. So there are some more tests on the insulation which you can do in addition to this. Now let me give you some details of these tests. Sorry if there is a lot of jargon there, and if you are not able to cope up, please feel free to ask that later on, because I'm not going into circuit breaker design in detail. So some of things, main contacts, auxiliary contacts, you will have to imagine. Um, I'll try to do my best. So first test which we talk about is the timing test. This is a very common test, which is done almost on all the breakers in high voltage. And what we are trying to do is we give the command to the coil. We simulate the relay command to the coil, trip coils and close coil, and we see when the breaker has operated. So it is kind of an overall test to see the overall performance of the breaker. That is the dynamic performance of the breaker, if it is working or not, and is it within time, which is the design parameter, or it is kind of stated by the manufacturer that this breaker will operate in 2 cycles or few milliseconds, whatever is the recommended window. It should work within that period. And then there are 2 sets of contacts: main contacts and auxiliary contacts. Main contacts, they have the main work to operate the main currents. Auxiliary contacts, on the other hand, have work to tell other logic or other part of the panel relays and all that breaker has operated. So both of them needs to be tested. And then there are a lot of sequences. So a breaker is expected to do open, close, close, open, and more sequences. And trust me, all of them are important and should be done at least during the inspection test, because some problems which you do not see in normal tests, you can see them in this complicated sequences, because here it really stresses the mechanical part of the breaker to its limit, and if there is any softness in the mechanism, it will become clear here. And also these tests are done in under voltage and over voltage condition to make sure that boundary conditions, the breaker should work satisfactorily in extreme conditions. So what we see as a result is some binary traces which indicates whether the breaker is closed or open. If it is closed, it gives a thick line. If it is open, it gives a thin line. And then this is for the main contacts. This is for auxiliary contacts. And also we record coil currents, strip coil currents here. So where we are giving the command, it comes here. This is the feedback which we get from the main contacts of the breaker. And we see the time difference between when the command was given and when the breaker operated. When the command was given, breaker operated. And that's how we do it, right? This is a very common test. And normally this is an indicative test for deeper investigation. There are, as I talk about investigation, coil current analysis is itself a very important part of analysis, because this will tell you what is the resistance of the coil, and if its moving part plunger is working properly or not, and all these things are kind of shown in the graph. And for analysis, normally we look back at the previous results to see if there is any change from the previous tests. The other powerful thing, which I frankly believe more, is to do the testing in under voltage and over voltage condition for the trip coil. There is a lot of text on this slide, so I will just focus on this picture for simplicity's sake. So these are the coil currents which were coming at different voltages. So we did at UN, that is the nominal voltage, at 85%, at 80%, 75%, 70%, and also in 125%. So all of them we did and superimposed them on each other. And then we could see that the breaker timing really depends on this coil current. And in some cases, some coils failed to operate in under voltage condition, which should not be the case. So they were kind of out of their design specs and needs to be replaced. So that's a much easier way to find problems. And you don't have to do anything else. You just need to change the voltage on which you are operating it. I see that there is some raised hand. I can take a question if it is a quick one.
Anyone have any questions? Feel free to write or switch on mic and speak. No problem.
Okay, for the sake of time, I will continue, and you can ask your question later or put it in the chat. Yeah, I just want to emphasize this point again. I cannot stress it more that trip coil and closed coil are very important. They fail a lot. They are very weak as compared to the gigantic breaker, which are very rugged. They fail a lot. If they fail, the relay command will not operate the breaker, and that's a sorry situation. And you would not like to be caught in that situation. So better to have this test and make sure it works in under voltage condition. This will definitely show you if there are any problems. Sometimes there are in 380 kV breakers, there are separate coils for each phase, and you just, oh, sorry. Marwa? Oh my God. So, see, everyone is saying, hurry up, huh? So, sorry, they just forgot. So, yes, so where was I? So doing this test has shown us faulty or not faulty because they were working fine. Customers have told us that this breaker is working fine as normal as any other breaker, but when we did the test, it did not operate, or it operated with a lot of difference with other phases, and it was a clear indication for the operators to replace it before that breaker creates a problem in the network for them. So yeah, one key takeaway here. The other test, again done on coil, as I said, to check the force which is needed for the breaker to operate, is minimum pickup test. This is a different test. This is not an under voltage test. Here we are not checking the time. We are only checking the force needed for the breaker coils to operate. So I'll just show you a video where there is a coil here, and it is trying to operate the mechanism. So there is some kind of a moving part, plunger, which operates this latch, yellow latch. And this latch, once it dislodges, operates the breaker. We want to find the minimum force required for operating this mechanical thing. So what we try to do is we give voltage, low voltage, 25% of the rated, try to operate. If it doesn't operate, let it cool down for a few seconds. Then try again with the higher voltage. We go like this till the time we are able to move it. So I'll just start the video. You will see this operating, and you will also see the voltage profile that we are using to operate this. So at some point, yeah, finally it operated, and then that's where it stops. So we get to a point where we get the voltage, and this voltage should normally be less than 60%. That's general recommendation from my side. Normally, people accept at 70% also, but that's okay. But 60%, it's good. If you, because these things are not so expensive. They are, as compared to the breaker or the kind of expenses that you would need to incur in case it does not operate, are huge. So yeah, 60% is a good number to, be safe. So this is other tests. So you saw we did so many tests on coil itself. So that's a big part there already. Then the next part is the motor. As I was saying, that motor has different mechanisms, very complex mechanisms, which needs to be lubricated. Especially vendors give their recommendations, and over time they are not. Sometimes it is not easy to follow them. So as an operator, you should know if this mechanism is good enough. So we check the current drawn by the motor to charge this whole mechanism, and the profile can be different. It's very vendor specific. There is no easy representation. Normally the vendor gives the normal charging current, inrush current, and charging time to give you the to help you do the analysis. But you can also look at the profile, which is good for comparison in case there are problems. So here I will again start a video where this will work. It will operate, and we will simultaneously see how the current profile looks for the motor. Okay, so here you see there was a high inrush current. If the lubrication is less, this current will increase, and there are limits where if it exceeds, you have to replace the mechanism. And then there is a wavy signature which was coming because of the typical design which was here of the moving part, that lever. So it's very difficult to know what is the RMS value here, but we calculate on a window the RMS value, whatever it may be, and we show it as for you to compare, and also the time taken. Again, this test is better to do it in under voltage and over voltage condition of the motor limits to make sure this will work in all conditions while it is in operation. Well, when we talk about timing test, I have to mention something specific for GIS, because it is very big topic in our region. And for maintenance, we cannot open the ground, and like the body is permanently grounded, or the contacts are permanently grounded when it is taken off and earth switches are connected. It is permanently grounded system, and it has to remain like that. We cannot open it, or we should not open it until and unless proper measures are taken to avoid any high voltage coming on the contacts, because the creepage distances are very small, and there can be capacitive coupling on these disconnector switches, which can be hazardous. Like 1000 kV can come across the, if this link is opened, 1000 kV can come easily here. So even if everything is de-energized and like the whole bay is de-energized, but still because of nearby active parts, it can come. So ground has to be connected, has to remain connected. And for testing, it creates a problem for us that whatever signal we send for testing those breakers to know the main contact feedback, it will always get a feedback from the ground that the circuit is complete, because the ground is very, very low resistance ground in a GIS. So we will never be able to use the conventional methods for knowing the feedback of the main contacts. So whether the breaker is open or closed, ground is always connected, and resistance is comparable to the contact resistance of the breaker. So yeah, the conventional methods cannot be used. And what we do in this case is we let the ground switch connected, no problem. And we put an inductive coil across the grounding loop. So this is grounding of the GIS, the grounding links from a GIS. This is example from Siemens drawings, but you will have different designs for different breakers and different voltage level. Like if I give examples of Hyundai or Hyosung, they have like 110 kV in Saudi Arabia. They have all the three phases coming out, and a strip bar is there. And for 380 kV, they have individual tanks for individual phases. So they have different grounds. So whatever the case may be, you can just put these ground links on that the external ground switches which are coming, and this inductive loop will measure the current going through the ground, and it will only measure the change. So when the breaker opens or closes, the current through the ground changes, because when the breaker is closed, current is divided between the circuit breaker and the ground, and when the breaker is open, all the current is routed, test current is routed through the ground. So we check that change of current, and that gives us an indication that the breaker is operating. And this is a very sensitive measurement because we are measuring like change of few tens of amperes, and it is happening while the resistance, the arcing contact resistance are also there. So the signal which we get from these current sensing loops are also can be used for analyzing the arcing contact length if we do it with the travel measurement. So a lot of analysis can be done without opening any ground, and this is good because in a GIS, opening a ground is a big topic, needs a lot of clearances. So if we can avoid that in inspections, that's good, because then if this indicates that there is a problem, then we have the justification to make that extra effort to take a shutdown and do a proper analysis of the contact health and the condition of the breaker. So also, like when you are doing inspection, you have to test all the bays. So let's say there are 50 bays and only 1 or 2 of them show some deviations in timing, then you just have to take shutdown or a longer shutdown for those two to do that, remove that ground link and do that extra effort for testing. So yeah, this is something which is quite useful for GIS. Okay, and the other challenge with the GIS is that there are CTs inside the current path. So when we are injecting through the ground loop, CTs are there, which also get the DC current in the primary circuit, and that can cause some kind of residual magnetism in the CTs, which we need to clean them. And sometimes it is not easy to open the CT secondary box to clean them. So if we can clean these residual magnetism with primary injection itself, that would be great. So there is a solution which is available to clean these CT residual magnetism, injecting a pulsating current in the primary circuit, which will clean them or reduce the residual magnetism, because otherwise this will give a false indication or it may lead to maloperation in differential protection. So yeah, it can better if it can be cleaned. So that's something which we need to take care when we are doing again these tests, to make it non-invasive, to not to open any circuit or to open CT secondary. Better to do it with the primary measurement itself or primary circuit itself. So that's all related to timing and GIS. Let me also skip one more timing thing, because again, there are a lot of different types of breakers. There is one specific type which I'm not sure you have in your system or not right now, or have you seen them in your studies or not. There is a medium voltage GIS systems which are coming. These are mainly used for primary and secondary distribution, where everything is sealed off in SF6 and there is no way to connect. There are no grounding connections on both sides. There is only one ground. So the method which I was talking about used both the grounds. This breaker only has one ground on the bus side, nothing on the line side. So they have a voltage detection system which we can use for measuring the timing of the breaker. So we do this test in online condition, because nothing can be done in offline until and unless you have to do a lot of preparation. Idea is to do non-invasive measurements, to do it very quick and easy. So they have these voltage detection systems which give voltage from these capacitors which are mounted in the bushings on the line side. And we take that signal and see when the voltage dies off. When the voltage is not there, that means the breaker has opened. When the voltage appears again, that means the breaker has made the contact. So with this, we can make the connection, or we can make the measurement. Again, as for timing measurement, we need to know when the command was given. So this is online. We don't give a command. We just keep a cable parallel to the command which is coming from the relay, and we just trigger our equipment based on that command so that we can start the timing measurement. So again, very useful for such medium voltage GIS, if in case you happen to see them in future. Another test which is commonly done on timing is first trip test, which is used to test the delay which is there in the timing measurement after a breaker operates after a long time. Here we use CT secondary, and instead of voltage as we were doing in the previous slide, here we take the current from the CT secondary while the breaker is live, and we take the voltage which is coming from the station as a trigger, and we do the measurement again in online condition. This is only done for tripping because in a lot of cases when the breaker is not operated for a long time, the grease and everything is hardened, so you don't get a chance to see that effect of that grease once it has operated for the first time. So yeah, so a lot of timing tests.
Sorry.
Yes.
You
Yes.
can, because now maybe 2 minutes to the 1 hour. You can speed up the presentation.
2 minutes or 10 minutes?
2 minutes.
Okay. My watch shows 8:50, so no problem. I was pacing for that. 2 minutes only? Okay.
It's no problem. 5 minutes if you.
Okay. I'll try to speed up. So the main thing in non-invasive is that it has to be like timing measurement has to be done. The other thing is contact resistance measurement, which basically tells us the resistance offered by the contacts when the breaker is closed. So main contact resistance. Hey, we do that by injecting high current, typically 100 ampere, and measuring the voltage drop across those contacts. And by current and voltage, we can measure resistance. So that is again very easy. Arcing contacts is something which is quite typical and which deteriorates also quite fast. So we see contact resistance. What we do is in dynamic contact resistance, we measure the resistance while we operate the breaker. So we keep measuring, we keep injecting current and measuring voltage and simultaneously operate the breaker so that we see the resistance profile over time, and that shows us the arcing contacts also. So if there is any problem which is coming there, you will see it, and trust me, there are this is like opening a Pandora box because you don't see them normally in all the other tests, but when you see them, they tend to surprise you. The other test is the travel measurement. Again, the standard mentions this test to be done, and it reveals mechanical defect in the kinematic chain. So the timing test gives us the timing of the mechanism. This gives us the distance it travels and how fast. So we can also see the speed in arcing zone. Because I'm talking to engineers here, they will not like the presentation. So I've given an example here. So this is a typical example with which I will finish my thing. So this is a typical example where a breaker is opening. This is the main contacts, auxiliary contacts. This is the travel curve, and this is the coil current. Now, when we do the analysis, we want to know the speed of arcing contact in the or the speed of the breaker during the arcing period. That's most important, and that happens when the breaker contacts open and for some more time, because in real life condition there will be arcing happening there. So there is a phase where it accelerates and a phase where it dampens, it slows down. So what the CIBANO brochure says for non-invasive methods, that you have to measure the make break distance the speed and the total travel, and also the reaction time, the time taken for the breaker to operate, start reacting to the command which is coming, and the time the mechanism takes to open. So all these parameters are important and should be recorded. So when we look back here, we see that total distance was 260 millimeter. Then we saw the arcing zone, and with that we take the corresponding points on the curve, that is 230 and 110, and then we calculate the average speed here, that is 5 meters per second. Also we can measure reaction time, contact pipe. So that's it. So I'll not go into details. I would say safety is important, GIS testing is important, and built-in supply which can be regulated is important for doing a good job while inspecting high voltage AC circuit breakers. With that, thank you very much for your attention, and I would be happy.
Thank you, Mr.
Take any questions.
Very much,
Yeah.
Engineer. Thank you for addressing this interesting topic. And now, anybody have any questions? Can just switch your mic on and speak if you have any questions. Engineer, if you have, if you want to write your email in the slide.
Should I put it in the question in the chat? Is that okay?
Chat, no problem. Yes.
Okay. Okay. This is my email address, and I'm also leaving my phone number.
Thank
you can contact me on WhatsApp in future. Thank you very much.
Maybe nobody to ask. You can now close the. Thank you, Engineer, for this interesting topic, and inshallah forward to another topic in your field. I know
Definitely.
that the Omicron have many interesting topic. Inshallah, we'll inshallah in future we'll see you for another inshallah topic.
Thank you very much. Thank you for having me. Thank you.
Thank you.
Looking forward. Thank you very much. Have a nice evening. Bye-bye.
About now in for recording have in YouTube, you can return to it.
Okay. Thank you very much. Thank you.
Thank you.